Okay, so this next type of problem is also a super typical problem. You'll encounter this a couple times this semester, and then if you do take calculus, this is a problem that comes up quite a bit in calculus. So it's an open box with a square base. Okay, so in other words, think of a cardboard box, think of an Amazon box, but cut off the top. So it's open in the top, and then the bottom is a square, but it doesn't mean that the entire thing is a cube. Okay, so I did my best to draw a 3D version of the box. It says the bottom is a square, so I'm going to call that those sides X because I know that the square has all sides the same. And then I don't actually know how tall the box is, so I'm going to call the height of the box Y. Okay, and then we know that it has to have a volume of 10 cubic feet. So that is something that is given, and that's going to be our constraining equation. Cubic feet, or like feet cubed, okay, 10. And the volume of a box is simple, and that's why they're giving you problems like this, right? You want to take the area of the base, just x times x, and then multiply that by the height of the box. So it's just a 3D calculation. So the volume of a box is basically the base times the like the length of the base. Maybe we could say length times width times height would sound best. Okay, so let's try that again. Length times width times height. Okay, so in this case, the volume would be x times x, which is x squared, times y. So what we know is the volume is 10. So 10 is equal to x squared times y. Okay, so like we did in other problems, we're probably going to need everything in terms of x. So let's solve this equation for y. So in other words, divide both sides by x squared. So y is equal to 10 divided by x squared. Okay, so now it says in part A, determine or express the amount of material used to make such a box as a function of the length of a side of the square base. Okay, so I did call the base sides X. All right, and it says the amount of material. So I think I'm going to flatten this box out so I can see it better, right? So this side is X and this side is X. That's the base. And then I have 4 rectangular sides. Okay, imagine I just took scissors down each of these lengths and just flattened it all out so that I could see the material. So this side, in other words, is Y. This side, of course, is X. These are all rectangles. And these rectangles are all the same size. Okay, so this is also Y here. Running out of room a little bit, but this is Y. And then the final one is here. And notice there's no top to the box. So it's just the base and 4 sides. So there's 5 sides of this box. Okay. So the material, that means that we want the area of each piece of cardboard, right? So let's do the amount of material. They called it A. And first, let's just do it in terms of X and Y, and then let's substitute in for Y, okay? So A, let's do the base first. That's X times X, X squared. And then we want to add on the rectangles. The area of each rectangle is X times Y, right? And there are 4 of them, so 4xy, okay? Now, if we want to do it in terms of x, which is what they're really asking, this is part A now. They're asking as a function of the length x. So we only can have x's, we cannot have y's in our equation. So x squared plus 4x, and then for y, we need to substitute in what we know about y. And that is what we came up with right here. So y is 10 over x squared. So let's put that in. So y is 10 over x squared. Okay, and then let's simplify that a little bit. So the a of x is equal to x squared plus, then we have 4x times this 10 over x squared. So 4 times 10 is 40. On the top we have 1x, and on the bottom we have x squared. So hopefully you can see that that would be the same as 40 over just an x. Okay, and that's our equation for the amount of material in terms of x. Okay, so it says B, how much material is required for a base 1 foot by 1 foot? Okay, so in other words, in B, they're saying, hey, let's say that the base x is 1 foot, right? So how much material is required? Well, that's simply plugging that into our equation. We're going to find the A of 1. So 1 squared plus 40 over 1. So in other words, 41. Now this is how much material, so this is the area. So this is in square feet. Okay. In part C, it says how much material is required for a base 2 feet by 2 feet. So in other words, x is equal to 2 feet. So we're finding the A of 2. So that's 2 squared plus 40 divided by 2. So that looks like 4 plus 20. So 24 feet squared. Okay. And you might be thinking, well, how strange that the base is 2 feet squared and now the area total is smaller, right? So if you question that, good, that means you're thinking about your answer. I put a smaller number in for x and I got a larger area. I put a larger number in for x and I got a smaller area, okay? Why is that happening? Is it wrong? Okay. So what I think is you have to think about the fact that the volume is always going to be 10 cubic feet, right? So the volume is constrained on this box. So the box doesn't just keep getting bigger and bigger if the base is bigger, right? Now the base is bigger, but that means the sides have to be that much smaller. So because the volume can only be 10. So then all 4 of those rectangles are smaller. And so that's what's making the total area smaller. Interesting, right? All right, so it says use a graphing utility to graph the area. For what value of x is area the smallest? Okay, so in other words, this is a minimizing problem. But if you think about it, this would make sense for a company to use because they know that they have to fill a box. It has to be 10 cubic feet large, but then they would want to use the smallest amount of packaging that they could because, they're paying for all the cardboard to surround it. So it's kind of the most efficient box. Okay, so we have to go to our calculator. It said use a graphing utility, which probably means that maybe it's not a good number. So let's just see. Okay, so I'm going to type in, here it is, x squared plus 40 divided by x. Okay, hit enter. And then hit graph, and then let's see how that looks. Okay, what you might be seeing is like kind of what I see, this line on my graph. But I think that's because, we need to see where the bottom is. We're not seeing the whole graph. So what I like to do is change my window. And I'm glad this happened because, it's going to happen to you and you're going to wonder what to do. Okay, so I feel like we're seeing all the x's. So I think it's more the y's. The x's, we see the graph, maybe it comes back up, I'm not sure, but we definitely need to see more of the y's. So let's, did I graph that wrong? X squared plus 40 over x, okay. So go arrow down until you see the y's, and let's go with a smaller y. Let's go to, I don't know, -50. And let's go to a larger y. Let's see, positive 50. Just so we can see a little bit more, because we know that the y value, right, in this case, it's not really y, it is the amount of material, okay? And we already know that with a 1 foot base, we have an area of the material is 41 and the other is 24. So we need things like, I picked 50, but you probably could have picked 100, okay? I hope you can tell I was just making a guesstimate, okay? And if it didn't work, I was going to try other numbers, okay? But now I see my graph and it looks so different than before, right? Wow. Okay, what a difference a zoom makes. So now we've zoomed out a little bit on this picture and we can see that, yeah, there is a minimum. Okay, now let's draw this graph a little bit on our paper and talk about just a little bit. Okay, and then we can easily find the minimum using calculate. Okay, so this whole part of the graph is basically nonsense, right? We don't want x to be a negative number. X is the length of the side of the base. It can't be negative. You can't, that makes no sense, right? So the only part of the graph that's really useful is this part that looks very interesting. Bit of a curve there, and then it has this minimum right here. So we are looking for what that minimum value is. Okay, so let's just calculate the minimum. Second, trace means calculate. We want the minimum, which is 3. And then we need our left bound and our right bound. So I need to get over a little bit closer to the minimum to make sure I'm in the right area. Now I'm on the left of the minimum, hit enter. Make sure you head past the minimum to the right and then hit enter again. Hit enter a third time for your guess. There we go. A minimum that really does make sense. So the smallest amount of cardboard that you can use is that y value, and the base length is that x value. Okay, so let's write that down. The x is equal to 2.714, and the y is equal to 22.104. Okay, the x, what they were asking for? They're asking for what value of x. So this is the answer right here. And this is the answer if they were asking for what is the amount of material, the 22.104. And of course, since that's an area, it's in square feet. Okay. So a nice challenging problem for us.